the recording as well. So I was happy to chat with folks after class about how the labeling of what is level 1 versus level 2 versus between versus within applies to you, because this can be tricky. So I wanted to start with that idea because it sounds like several of you are going to be working with a data set that does not conform to this layout. So last time we started talking about vocabulary and describing longitudinal data. And to me, the definition of longitudinal is that it is a sampling unit, more than one, hopefully, but at a minimum, just one, that is measured repeatedly. So single case designs where you have like one subject and you make them do things and then you make them do different things, that's longitudinal data. In that case, you wouldn't have a level 2. You wouldn't have inter-individual differences if you've only measured one subject, but you certainly do have within subject variation as a function of condition or time or what have you. So longitudinal has to be the same whatever measured repeatedly. Panel studies is a synonym for longitudinal data that gets used in econometrics and sociology. And I think some of the EPLS folks were nodding, seeing that panel data. Have you heard that before? Interestingly, I have recently become a little bit more well-versed in the language that goes along with that, because there's a whole debate about endogeneity and fixed effects versus random effects that actually maps directly onto the same concerns that we'll talk about with respect to level 1 predictors that vary over time. So that will be coming this semester as well. But in terms of the questions I had in office hours, what if you have different people at each occasion? That was the question that I had. So if you have a survey where every year they send out a survey to measure sort of the status of whatever, but they send it to different people, that is not longitudinal. However, what you can do in that case is think about differences between years, and you could look at the effect of time, whether the mean response of some outcome changes as a function of year, and whether or not the relationship between predictors and outcomes as measured within a given occasion, whether that relationship differs by year. So is behavior more strongly related to attitudes early on than later in the study? That kind of thing. You can still answer those sorts of questions, but in that case, it would be more accurate to think of year as just any other kind of grouping variable, where you have people from different groups, and a group is the year 2000 and another group is the year 2001 and so forth. So that kind of design where people are not repeated, to me, is not longitudinal. It is cross-sectional. And to the extent that you want to be able to talk about change over time in the means of the outcomes or in the predictors, you really do have to believe that you have the same type of sample, that you've achieved the same type of representation at each occasion, because then that's an obvious confound if it's different people at each occasion. So that's more of a sampling design kind of issue. So does anyone else have longitudinal designs that they're thinking of or interested in learning about that may or may not correspond to this sort of simple two-level demarcation of within persons and between persons? Yes. Is that a yes to that question or a yes to something I said 5 minutes ago?
That was 5 minutes ago.
Okay, sorry, Nikki. Do you want to say something about that?
No, it was literally just said, you said some EPLS students were using the panel term, and I was like, yes, that was me.
That was you. Okay, I remembered. Excellent. The world of multi-level models can be applied to any kind of sampling design in which there's more than one kind of sampling simultaneously. The particular design, though, dictates where the levels go. So if you're thinking about this in the context of clustered data, for instance, if you have, say, children who are sampled from multiple schools, then in that case, it would be level 1 is kids and level 2 is schools. Where you can make it a little bit simpler in your head is just drop the end of the word here for person. The labels between and within always work. It's between and within what? So in that example, if you have children within schools, it's between and within schools. In this class, it's between and within person, because within person means overtime. So between is always level 2, within is always level 1. The design then dictates what the adjective is that goes with that. And you can have other combinations too. So if you have a survey of countries where the same countries are measured over time, but they're measured by different people at each occasion, then people are level 1, occasions are level 2, and countries are level 3. So it just depends on the design what the levels are. But in the case we're talking about, what I'm going to try and focus on is sampling units measured repeatedly. And we are going to pretend, or at least start with the idea that the sampling units themselves are independent. So people are not from groups or things. If they were, we'd need a 3-level model, which is not where you start with week 1 of your class. Not even the advanced class starts with week 1 as a 3-level model. Because the doorbell is still ringing, that's why. All right, so any thoughts or questions over designs, levels, vocabulary, any of that before we jump back inside? I'm watching the chat window this time, I swear. Okay, fair enough. Then I would like to start with slide 14 in lecture 1. So I had a question after class, by the way. When I have like lecture 1, example 1, lecture 2, lecture 3, are these the same numbers that have occurred in other classes? And the answer is no. Each class has its own numbering system that's ordered by the topic. In this class, though, the assignment numbers are not going to correspond directly to the lecture and example numbers, which is why if you look at the syllabus, I've said based on which example each homework applies to. These do correspond to the chapters in the textbook. So lecture 1 covers chapter 1, lecture 2 will cover chapter 2, and so forth. So it is organized, just not quite in the way we're used to. All right, so we talked about change and fluctuation, and now we get to talk about synonyms. So slide 14 is where we're picking up. I want you to know what you are also learning by being here. So the terminology that I use to describe our longitudinal models is that I'm teaching it through a framework of multi-level models. Multi-level model means more than one kind of sampling at once. Kids and groups, occasions and kids, occasions and groups, some combination where it's more than one dimension simultaneously. Synonyms for this family of models include general linear mixed effects models. Mixed effects is a term that means you have both fixed effects, which is words that hopefully you already know because the intercepts and slopes from a regression model are examples of fixed effects. They are estimated constants that apply to every case in the sample, versus random effects, which are not constants, but they are variables. So there are effects that differ across sampling units. And so mixed means you have fixed and random at the same time. Linear means that it is a slope times variable plus slope times variable plus slope times variable framework. And general is actually a very specific word, which is sort of hilarious. General has a specific meaning that we are predicting outcomes whose residuals are supposed to be normal. So breaking down that terminology, the words mean something very specific, and it can be helpful if you know the right words to ask the Google about when you go trying to find models on your own. This same multi-level model or mixed effects model is also known as a random coefficients model. And random coefficients are the same thing as random effects, which are the same thing as latent variables, which is why we can do most of what I'm going to teach you using a structural equation modeling approach versus a multi-level modeling approach. And then finally, even though I'm in education, I don't use this terminology. I keep waiting for someone to yell at me, but it hasn't happened yet. Hierarchical linear models is the terminology that originated for these models in education. This is Steve Radenbush and Anthony Breich, I think, their writings starting in the mid 80s. So they were the ones who wrote the first textbook that was widely adopted. They wrote software, which is called hierarchical linear models, or HLM. So if you hear that terminology, that's this. It is not the same thing as hierarchical regression, which involves building a regression model in chunks where I add these predictors and then I add these predictors. That's not the same thing as this. So synonyms and then special cases on the bottom here. So you know the expression, if you have a hammer, everything is a nail? Have you heard that expression before? Well, I have been accused of thinking that everything applies to multi-level modeling as a bias, but it does. Everything is a nail. So once you have this hammer, we can hit anything we want, because all this stuff that you've seen before is actually a special case of multi-level models. So random effects analysis of variance, which is not something I was ever taught, but is a thing, or repeated measures ANOVA, which I was taught, that's what we're going to talk about next week. Those are special cases of multi-level models where you have only a random intercept. The latent growth curve model, or growth curve models, is when you're focusing on modeling average change and between person differences and how people change. The latent means you've done it in an SEM software package instead. Within fluctuation models, so we talked about that a little bit, the idea of sampling longitudinally where you're not expecting people to change. You just need a bunch of data per person so that you can look at how their predictors and outcomes sort of co-vary or travel together in time. Those designs have become very popular nowadays. Clustered or nested observations. So clustered data is the term when you sample people from naturally occurring groups. So if you sample children from schools, you sample patients from hospitals, you sample survey respondents from cities, that kind of thing where people are grouped and you can't really do anything about it. That's clustered data or nested data as it's known. So these models work for that. I'm teaching that class in the fall, by the way, if you're interested in learning that application of multi-level models. Cross-classified models is when you have multiple sampling dimensions that are crossed rather than nested. Molly says, it's a great class, take it. Correct, that is the correct answer. Yes, it is a great class and you should take it. We'll have a lot of fun. Cross-classified models. So these have become more popular in education under the label value-added models. Have you heard about these? Yeah, Katie's nodding. Few people. Okay, Kaylin's nodding very emphatically. Yes, we've heard of value-added models. They're ways of rewarding or penalizing teachers that rely on random effects. They're sort of bullshit, I will just say. They're only as accurate as the model that they come from, and we will talk about sort of the nitty-gritty of where those random effects come from, and then they should give you pause too once we get to that point. But also cross-classified models, like if you have a sample of children who come from different schools and they live in different neighborhoods, but not all the same kids who go to the same school live in the same place, and not all the kids who live in the same neighborhood go to the same school, vice versa. That's a cross-classified situation. What people may know of as explanatory item response models, where both subjects and items are random factors. That's a multi-level model, as is every other psychometric model that you may have been taught in your other measurement courses. Item response theory. Theta is a random intercept. Confirmatory factor analysis structural equation models. Factor scores, latent traits, latent variables, latent factors, whatever you want to call it, those are random intercepts as well. So everything is a multi-level model is what I'm telling you. So you're in a good situation. I'm going to focus on the particular application of multi-level models to longitudinal data. So this is a longitudinal class because there are things you have to worry about when you're sampling over time that you don't have to worry about when you're sampling just over people in groups. There's an extra levels of complexity. And so that's why I've broken this down into this purpose of multi-level models for longitudinal data this semester versus an alternative purpose for grouped data, clustered data as it's known in the fall. Okay. Questions, comments on any of those synonyms or any that I should add to my list? Are there any others you've heard of and wondered, is that the same thing as this?
I've got a question.
Sure.
How are clustered models different from just different groups of interest? So if your population is divided into children with autism, children with language delay, children typically developing, is that different from a clustered model?
Yes, it is different in the number of groups and whether or not you would control for group membership via fixed effects or not. So like in your example, if you had children who were nested in groups, say with an autism diagnosis versus without, once you put in that binary predictor for which group they're in, they are no longer clustered because you have controlled for group differences. But if you were recruiting from multiple sites and each site had a group of children with a diagnosis versus without a diagnosis, so you might have 6 diagnosis groups and 6 non-diagnosis groups, then just putting in a predictor for which group you're in is insufficient because you're not controlling for differences among people of the same particular group, not just the autism yes or autism no group. And so the question is whether there's group-related variability left over after you control for the predictors in the model. And if the answer is yes, then that variability has to have its own error term. And so that's the idea of multi-level models, is that each dimension of sampling has at least one error term that goes with it for unexplained variability due to predictors of that particular dimension. Does that help?
Thank you.
Sure. And the same thing is true, by the way, let's see, there's Jacob. He was the one who brought the example of people within occasions to me. And I asked you how many occasions you have, and you said 6. Is that correct? Or correct enough for our purposes? The reason I asked is exactly what Lane just said. If you have 6 occasions, you can put in 5 mean differences and you're done. Right, that controls for all occasion mean differences, and there's no more variance related to time that you have to worry about with respect to the intercept. You might have to worry about group differences, which is, it's the exact same situation, even though they're years, they're groups of people. You might have to worry about group differences in the slopes of predictors via interaction terms, but then you'd put in 5 of those and you'd be fine with respect to that too. So we're talking about fixed effects versus random effects more generally in this conversation here. Question, what happens when not everyone has the same amount of occasions? It's fine, is the short answer. We call that unbalanced data or incomplete data. Those are terms that we'll get to, but briefly, incomplete means that not everybody has the observations that were scheduled. Unbalanced means not everybody has the same possible observations. And either one of those is fine for what we're going to do, which is one of the reasons to do it, because it is not fine if you try to use repeated measures ANOVA, which has least squares, which is the problem. Does G theory also fit into the MLM framework? Why, yes, it does. G theory is a cross-classified model where you have raters crossed with subjects, crossed with items, crossed with whatever. Boom, everything is a nail. It's true.
I have a question.
Yeah.
Is making something is giving something a random effect or including a random effect, is that the same thing as adding like a level 2? Is that what you're saying?
Yes. So,
and that's the same thing as adding an error term for that. Okay. It's
yes.
like equals, equals, equals.
Yes, yes, yes. Adding a level means adding another kind of leftover variability. So at the lowest level, they're called residuals, and at the higher levels, they're called random effects, random intercepts, and random slopes. But they're all error terms because they all are reasons why not everybody did the same after controlling for predictors. Why don't all people have the same mean? I don't know. That's between person variance, which we're going to use a random intercept for. Why does a given person have a different outcome on a given day? I don't know. That's within person variance. We're going to have an error term for that too. So yes, adding a level means adding a source of error unexplained variability, which gets a special name as a random effect for higher levels than the first one you started with. Yes, I told you vocabulary. Did I not warn you this on Tuesday? That it was going to be like synonym soup? And I know it's like overwhelming, but if I only taught you one set of words, then you would only be able to read some articles. And so knowing how to speak across the codes that, oh, this is this, this is this will help you. All right. Other questions, comments? Okay, then moving on to slide 15. So an overarching framework that I'm going to use to talk about what goes into these models is that every model on Earth has two sides. There is what I call the model for the means and the model for the variance. The model for the means is what I guarantee you think of up to this point when you think model, particularly in the context of general linear models, regression, and so forth. It's okay, how do the fixed effects combine with their slopes to create some sort of expected outcome? Which predictors go in the model? Do they need main effects or do they need interactions? That kind of decision refers to the model for the means, where the goal is to create a predicted outcome for each case. And the way that we do that is by estimating constants as multipliers of the predictors that we call fixed slopes, where the term fixed means it is a constant that everybody gets the same. There's a whole other thing, though, that I kind of wave my hands at a little bit in 6242 that is the whole point of this class. Fixed effects are all observed variables, correct. You have to have a measured variable in order for it to have a fixed effect. In the world of structural equation models and path models, you could think of the paths between latent variables as fixed effects as well, but I don't want to get into that sort of confusion. But yes, for our purposes, they multiply observed variables. The other side of the model, though, is the error part of the model. If you want to sound fancy, don't say error, say stochastic. That means error in fancy. But we're talking about the random effects and the residuals, meaning how does the model predict what all goes into the variability of the outcome, and more importantly, the covariability of the outcome across observations. So when you learned your first regression model, general linear models, whatnot, there was a letter here, this way, at the end of the equation, right? Do you remember what letter that was? It's going to be one of two letters, I can guarantee it, depending on who you learned it from. E, alternatively. Anyone else give me another one they learned at the end of the regression model? No one else? E has it? It's E in my book. It's also R for residual. But you were told, right? It was in there the whole time. Even a model with no predictors, an empty model, had an E or an R at the end of it. And you were told that in order to use this model, those E's or those R's have to have three things be true about them. Do you remember this? They got to be normally distributed. They got to be independent, which is the big one here. And they got to have constant variance. Or else, right? Then you can't use the model. And you can pick a new model if any of those are broken. But the whole point of this process that we're going to go through is it's really focused on that aspect of the model for the variance. When you have multiple occasions from the same sampling unit, at a minimum, you got to have two different kinds of E's, because you have the E's that describe why some people are higher or lower than other people. That's level 2, between person, inter-individual differences at the macro level 2. And then you have why aren't all occasions the same within a person? That's another kind of error variability. And that's level 1 within micro, intra-individual differences and time varying. If you had people who were measured repeatedly over time, and those people were nested in schools, okay, I need a third kind of E for why are some schools doing better than other schools. And if those schools are nested in districts, I need 4 E's, right? Because some districts do better than others. Question. So all random effects will get a distribution while fixed effects don't because they are observed close. Random effects will have a distribution. The distribution will be normal, by the way, whether you like it or not. Random effects are almost always assumed normal, and research suggests that it's okay if they're not actually. It's hard to tell. Fixed effects are not observed. They are estimated by the model, but they multiply observed variables. So the fixed slope is the multiplier of the observed information. But fixed versus random. So we're going to spend a lot of time trying to figure out if we have the right model for the variance in terms of making sure that we've got enough types of e's for all the different kinds of sampling that accurately characterizes how the observations from the same unit relate to each other, either in a constant correlated kind of way or in a non-constant kind of correlated way. Can everyone put questions in the window for all to see? It's up to you. So when you enter into the chat window, there is an option that says send to everyone, or you can send messages only to one person. So you can send notes to me that only I see, and I try to read the questions aloud so that I don't miss if someone didn't get to type it. So some of you are sending things directly to me and some of you are not, and it's fine to do whatever you like. I will warn you though, if you're in other situations, not to talk smack in the chat window, even if it's not going to everybody, because if the session is being recorded, there's a transcript of the chat window. So just as a heads up, Zoom etiquette, like take your smack talking offline into another mechanism, right? So not that any of you are talking smack, and I'm not recording the Zoom session, I'm actually recording the stream, which is a different thing. So you can talk all the smack you want, it's fine. So anyway, point being, this idea of how many kinds of error variability we need, that's the model for the variance, and that's the primary way that multi-level models differ from the single level regression type models that you know already, is that you didn't have to worry about that before and now you do. So more words then to try and map onto, there's like a two-dimensional space that we can talk about with respect to what models are called and what their assumptions are. And one of the dimensions then is general versus generalized. So general means that these are both single level models. So those words describe models that are for independent observations. General means the residuals for that one single level are supposed to be normal, and generalized is some kind of not normal. So special cases of that go with, for binary outcomes, that's a logistic model or a probit model. For count outcomes, that's a Poisson regression or a count regression, ordinal regression, gamma regression. There's all kinds, right? There's a different kind of regression for any kind of outcome. So long as you've got a probability function that goes with it, you're in business. So general versus generalized. Generalized linear models is coming back a year from now. So the next spring, if you want to take that, focusing on models for predicting outcomes that are not normal. The dimensions of sampling then gets introduced with the addition of random effects beyond fixed effects. And so then when you get into multiple dimensions of sampling simultaneously, then there are mixed extensions for each of those cases. So we're going to do general linear mixed models in this class, meaning all the residuals are supposed to be normal, but there are also generalized linear mixed models for binary outcomes that are longitudinal, count outcomes that are longitudinal, and so forth. So these are the dimensions that I would recommend searching through in terms of how to describe, like, how do I know what kind of model I need? First question is whether or not you have one dimension of sampling or many, and then whether or not the outcome is something that could plausibly be normal or not. And also a very good class. Thank you. Molly is going for the points today. Yeah, generalized is fun. That was the one we did last spring where I didn't, it was a brand new prep for me and the pandemic happened. And so I got to become real efficient as the semester went on. What is the difference between conditionally normal and conditional? The term conditional means after controlling for predictors. It sorta is the same as residuals, but in non-normal outcomes, people don't use the term residuals as much. So conditional means whatever is left over. Conditionally normal then is a particular kind of conditional. If it's binary, it would be conditional Bernoulli. If it's ordinal or nominal, it would be conditional multinomial and that kind of thing. So this is to say we're focusing on normal land, but if you've had the generalized modeling course or you've done those kinds of models, then so long as you know what a logit is or a probit or whatever you're using, you'll be good to take that content and stick it onto my content and you'll be just fine. And I have examples that I can send you if you want. So latent variable models will be generalized linear mixed models. Latent variable models, if you're in like CFA where everything is normal, that would be akin to general linear mixed models. IRT is a generalized linear mixed model. Yes, good connections. And for those of you who are sitting there going, I haven't had these classes, what the hell are these words? It's fine. I'm just trying to make the connections for those who've had them, and you will get them eventually too. Yeah, the hardest part about all of this is figuring out how it fits together. Once you can do that, then organizing these things in your head gets a lot easier. Okay, so then the question, are we going to learn latent growth curve models in this class? Yes, I'm just not calling it that. The reality is that the models that we're going to fit can be fitted in most cases equally well in structural equation modeling software as single level structural equation models versus regression type software like SAS and Stata Mixed as mixed effects models, because random effects and latent variables are the same thing. I have made a choice to teach the content from a multi-level modeling perspective because I think it's an easier ask. Because I can start with regression and get you moving in these things, whereas if I'm teaching it from an SEM perspective, you had to have all of that content to figure out how a special case of SEM is tricking it to do this analysis. So I just think it's easier to learn from scratch from a regression kind of way of thinking about it. Now, that being said, there are certain situations in which you have to do it the SEM way, and certain situations in which you may have to do it the multi-level way. SEM is better for adding on latent variables. So if you have a measurement model of items that create a latent factor and you want to watch that latent factor grow in a simultaneous analysis, that has to be in SEM. If you want to do mediation, where this thing predicts this other thing and that thing predicts this thing, and each of those things may grow, that needs to be done in an SEM framework as well. So we'll get into those distinctions the last week or two of class, but we're staying in regression, multi-level, mixed effects kind of world for the time being. And then, yeah, there's multi-level SEM, which in most cases is just actually multivariate multi-level, and it's not as hard as it seems. So we'll get there. All right, so my sales pitch, in case anyone is thinking of bailing. I want to give you the sales pitch for why this material will be useful to you. What can MLM do for you? And no, that does not stand for multi-level marketing, although it kind of could, because I'm sort of putting on my infomercial vibe here. But that's not all. If you act now, you can secretly learn cluster data analysis at the same time. So what can this do for you? Here are my 4 talking points. I'll hit each of these in turn here. So dependency. So you are told that in regular regression land that your residuals are supposed to be independent. Well, the opposite of independent is dependent. That word just means correlated. That's it. It's a term that implies there's something wrong. Like I have dependency in my data. But dependency is the point of collecting longitudinal data, to be able to look at how patterns happen over time and how people differ in those patterns. So dependency is not necessarily a nuisance. It's the thing to be studied. And the nice part about multi-level models is that you can kind of think of them as tinker toys. Like you can attach things together in whatever way you need to describe your sampling variability and all the different levels crossed versus nested. So you can have nested dimensions, which is what we've talked about mostly up to this point, time within person, person within cluster, trials nested within persons, for instance, in an experiment. And if you're sitting there thinking, okay, which is nested in which, and you're not sure which way it should go, that is a dead giveaway that you actually have a crossed sampling structure and not nested. So persons and items is a great example. If I make everybody respond to the same items, then each individual response is nested both in items, because responses to the same item are probably going to be related because of whatever characteristics there are of that item, and responses from the same person are going to be related because of whatever characteristics of that person. Persons and items are crossed. So in that case, you'd have two different kinds of level 2s. You'd have between persons and between items, and your within would be within persons and within items. So if you're unsure how something works, it may be crossed and not nested, and that will help you try to figure out where the effects need to go. And then this last bullet we talked about earlier, in order for something to be a level, meaning you need an extra error term, meaning you need an extra random effect, there has to be unexplained variation remaining after the predictors. So just 2 groups is not sufficient. If you had 20 groups and you put in a control versus treatment or diagnosis versus not, then you'd have group variability left over. You got to worry about it. That's the thing. So to control for group via fixed effects is an option in which you would take your group ID variable and turn it into a predictor. That is what's known as a fixed effects approach, and that is useful if what you really want to know is what happened to each individual unit. But if you want to know why some units are higher or lower and you want to predict that variability, then you need random effects instead of fixed effects. All right, questions. I'm going to pause and reload here. Okay, so reason number 1, model whatever pattern of dependency you find yourself facing. In longitudinal data, there are 3 different kinds of dependency that can exist. There's probably more, but this is sort of my way of thinking about it, and there's 3 different ways we can tackle it. So there's mean differences across people. If you measure people repeatedly over time, some people are just going to do better and some people are going to do worse. That causes a constant dependency, a constant correlation of occasions from the same person, and that is what we use a random intercept for. Question. I thought fixed effects was not about the individual cases. I thought random did that. So a fixed effect, actually this is a great segue into where I am. Fixed effects versus random effects. You can either estimate, if you have say n groups, you can estimate n-1 fixed effects. That would fully saturate, each group would get its own intercept. And then you would know specifically about group A versus group B versus group C, but you couldn't then predict why A is doing better than B with predictors. So if you want to focus the inference on what happened to an individual unit, you want a fixed effects. If you want to predict why some units are doing better than others, then you need a random effect, because what you're really doing is using the random effect to capture unexplained reasons. Okay, does that help? There's too many of you. I'm looking for someone to nod. Say, where'd you go? Okay. As another example of fixed versus random effects, by the way. Oh, Kelly has a question? Okay, I'm waiting.
I'm trying to figure out how to ask it. So like if you don't really care, like it's more so a nuisance, like I just need a control for this, that would just be fixed effect. And if you actually have a question about it, like you want to know why it affects them over time, that's when it'd be random.
Yes.
Okay. All right.
Yeah, it's 2 different reasons to have a fixed effects model. Is it because you care about individual units in particular, or you just want them to go away? You just want to like control for it, push it aside, know that that's not a reason that you have to think about it. Conventional wisdom suggests that you need so many units before you should do random versus fixed. 10-ish or 15-ish, it's very hard to estimate a variance across very few units. So if you really want a shot at being able to quantify how different your units are, you need at least like 30, 50, somewhere in there. And from the perspective of prediction, yeah, I mean, if you have predictors that are unit level predictors like person things, the more people you have, the more power you have. If you only have 6 people, you're not going to predict anything anyway. So you may as well just fixed effect it out. All right. So random intercept versus fixed effective ID. Both of those things would control for mean differences across your sampling units. Let's just go with people here. But only a random intercept allows you to then try to explain those mean differences, where the random effect would be variance left over. People also differ from each other, though, in effects of the predictors that are measured repeatedly, like time. If people differ in how they change over time, which is usually the point of doing longitudinal analyses, is to watch how people change differently and then to be able to predict why they change differently, that introduces a different kind of dependency that's non-constant. It's going to be a pattern of correlation that depends on which occasion it is. And so that is another kind of random effect that we need in our model that's known as a random slope. So the umbrella term random effect is the highest. Special types of random effects are intercepts and slopes. Intercepts refer to means or shifts along the y-axis. Slopes refer to different slopes as a function of some x. So you may need both a random intercept because some people are higher than others on average, as well as a random slope for time, which means some people change more than others on average. So that's 2 different kinds of dependency. And then there's a third, which I don't have a clever name for, but occasions that are closer together are often more related than occasions that are further apart. So we put in a pattern of correlation for the residuals that allows that to happen. So longitudinal data often need that kind of extra autocorrelation. And that's the kind of thing that doesn't happen in clustered data, which is why I say time adds a level of complexity, no pun intended, to what we're going to be doing. Okay, questions, comments on that? Okay, so why do we care about dependency? Knowing how people vary is sometimes a research question and sometimes not. Question from the audience. This is the same for spatial autocorrelation. Near things are more similar than far away things. Yes, very good point. So that in spatial temporal data, you have to worry about occasions being more related that are closer together, and then in the space dimension, things that are more related that are closer physically too. So yes, SAS has spatial correlation structures as one of the things you can do in ProcMix, by the way. Why should we care? Even if you don't care in terms of a research question what kinds of dependency there are in your data, you need to care in order to get the most correct tests of the fixed slopes, the things you do care about. So if you ignore dependency, if you ignore levels, if you take your longitudinal data and you stick it in a regular old regression, the slope estimates that you get out for your predictors are probably going to be okay to some extent. It's their standard errors that are messed up. And they'll be messed up in different ways depending on what level of the model they are. Level 1 predictors will have standard errors that are too big because they're going to be based on all the variance in the outcome and not just the level 1 part. Level 2 predictors are going to have standard errors that are too small because they have the wrong degrees of freedom, because you have these replicates that have the same exact score for their level 2 variable. So point being, ignoring dependency screws up your p-values for your fixed effects, and that's a reason to care. Knowing what kind of variation you have is also prescriptive from a model building standpoint as to what kind of predictors are going to be useful. So one of the first things that we will do in a longitudinal data set is figure out how much of the total outcome variability is because people differ from each other in their means versus differences within people around their means. In other words, how much of the total variability is cross-sectional, would have been there if we only measured them one time, versus how much extra variability did we pick up from measuring longitudinally. And we'll get a ratio of these things. It's called intra-class correlation, by the way, for those of you who've heard that terminology. And if we find out, say, that 80% of the variability is because some people are higher than others, well, then we know that the only way to explain that is by people things. Things that are constant to a person explain why some people's means are higher than others. If we find that instead 80% of the variability is within a person over time, then we need a different kind of predictor. We need a predictor that's measured at every occasion to capture that within person variability. So you have to have variability across sampling units for predictors that are measured for those sampling units to have anything to do. And so it depends, items, people, occasions, trials, whatever. The amount of variability that's due to each source then guides which type of predictors that are going to be most useful. All right, thoughts, questions? We're good? I'm sensing the energy level coming down a little. Well, not mine, of course. I'm hopped up on caffeine. But it's looking like it's 2:45 in the afternoon, I gotta tell you. Is that what I'm seeing? It's 2:45 in the afternoon? Yep, okay. Let me know if it's me, because I can live with it being 2:45. All right. Another reason why what can MLM do for you is that you can put in any kind of predictor you feel like. And I never thought about this much as a limitation until I started working with these models. And I turned a very crappy master's thesis into a token example for a multi-level modeling paper. In the world of ANOVA, all of your predictors are groups. You have between group differences, and if you have a repeated measures design, where each person participates in more than one condition, say, condition is a group variable as well. Or you can have a regression model where you can include predictors that are quantitative, that are more continuously varying, or grouping variables. But what if you have a repeated measures design where one of the repeated characteristics is not a condition that's discrete, but instead something that's quantitative? Then what? Repeated measures ANOVA isn't built for that. So that's one of the reasons why you might fit a multi-level model, meaning using proc mixed with maximum likelihood, is if you want to do a repeated measures analysis, but you have predictors that change over time. They're called time-varying predictors. If you have predictors that pertain to higher levels of sampling, you can include those too. So if you have measured children repeatedly from the same school, you can have school level predictors, you can have people level predictors, you can have time level predictors, you can have interactions between them, and each of those predictors can be grouping variables or quantitative variables or whatever you want. So the sky is the limit in terms of the creativity with which you can specify your model. Third, because people don't cooperate is why MLM works for you. So let me see, how many of you have longitudinal data that you've worked with before? Anybody? A few people? Couple people? Okay, those of you who have longitudinal data, did everybody come every time they were supposed to and do everything that you asked? Nope. In 15, 20 years of teaching these models, no one has ever said, yep, everybody came every time they were supposed to and did everything that they asked. One person tried to once. It was in psychology, and he's like, yeah. And I'm like, who are your subjects? He's like, rats. He was from the animal modeling lab, the biopsychology department at Nebraska, and he's like, yeah, the rats, they come whenever we tell them to. But I kept pressing because I knew that in this particular lab, one of the things they did was get their rats hooked on meth, cigarettes, cocaine, caffeine, stuff that's bad for you. And you know what happens when you get addicted to drugs? You die. The rats up and die on you, particularly at the doses where they're trying to see, what happens. Because drugs are bad, okay? That's a Mr. Mackey reference for those of you who are old enough to know what South Park is. Drugs are bad, okay? So even he had incomplete data because the rats die. And when you can't show up for your last session because you're dead, that's kind of the definition of not missing at random, right? That's informative missingness. So what they typically did, by the way, is go get a new rat and hope that one doesn't die. And then they have complete data. So I think he was interested to hear that that was, you didn't have to go through the life cycle of a rat all over again to make sure you had enough data. You could just use whatever you had. So even if you have just 2 occasions, even if your design is a straight up like pre-test, post-test where you don't have anything fancy and repeated measures would have been just fine, if you have missing data, then switching to this approach to modeling that changes the method of estimation and it changes what the definition of a case is will allow you to keep whatever cases you do have. So the magic happens in switching the type of data structure. When you estimate a repeated measures ANOVA like in SPSS, you're supposed to have the repeated conditions as separate variables, and each row is one person. So yes, a case changes its definition from a person to an occasion. So in this data structure on the left, which is known as wide or what I call multivariate, each case is a person. And any cases that don't have all of the information are gone. So even though person 101 had 3 out of the 4 occasions, we can't use them. And that's because the method of estimation here is least squares, where you have to have all the data to calculate the leasting, the sums and all that stuff. And if you switch to a data structure that looks like this, so this is what's known as a long, or I call it stacked. And if you watch my hands here, this is your tuition dollars at work. You get the extra show that's not on YouTube. If you take each row and do this, it's a row by row transpose. That's what's happening here. And by the way, this is 3 lines of code. So don't think you have to manually restructure this. Every program has a way to do this automatically, including SPSS. So the trick is that then we have a variable that holds the information that used to be across the column names as to which condition is which or which occasion is which. So now I have a new column that's called time, and I have a condensed column that I've called y, meaning the outcome for each of the previous y1, y2, y3, y4. And so any information that is person level gets copied down across the rows through this process, which it needs to be, including their idea, including sex, which is an example of a time invariant predictor here. And so what happens is that the same rules still apply. Any case that is incomplete gets kicked out. But now person 101 can have 3 out of their 4 occasions contribute because 3 out of the 4 rows are complete. So that's the trick, is that it's redefining what a case is. The same rules, though, with respect to missing data apply. Anything that is incomplete gets kicked out. The other piece of this is that people may not cooperate in when they come in. So they're supposed to come in at time 1, time 2, except that they were sick when it was time 2 and they had to reschedule. And by the time you got them in, it was more like time 2.5. So is it time 2 or is it time 3? You don't want to push people into the wrong box. You don't want to round time and introduce measurement error. You don't have to. So if somebody is measured at their own intervals, whether on accident or on purpose, because time is a variable, they don't have to be discrete. You can have whatever times a person has. Each person could literally have their own set of times and it's fine. So the term for that, by the way, is an unbalanced design. When people don't show up when they're supposed to, such that each person's times are distinct. So this is the reason. True story. I once had a student at one of the previous places I worked. I'll protect their anonymity by saying it that way. And she was not in my class. She came to the first class and not the second, and she was doing her dissertation, and she showed up at my office hours every single week for help on her dissertation. I was not on the committee. And I had her using proc mixed for this reason, because she had a sample where half of the people didn't come back at time 3. So she was going through her models and looking at things, and nothing was significant. Nothing was turning out the way it was supposed to. And so her well-meaning advisor said, you know what, I don't think you have the sample size for these fancy models. Why don't you just go back to repeated measures ANOVA? Okay, exactly. Thumbs down. All right, and I told her, you can do that. And now you just lost the other half of your people because you have to have complete data and you can't put in any of your time varying predictors. But it worked out that what she had in her model was only a random intercept. She did not have any random slopes. So from a mathematical perspective, she did have a repeated measures ANOVA. That is what she had. But she did it with likelihood estimation instead of least squares, which means she didn't have to dump her cases. So that's one of the reasons why I want to spend time on that. Looks like next week, hopefully we'll still get to that as to how these things compare to what people refer to when they say repeated measures ANOVA, so that you can answer those sorts of suggestions as to whether or not what you're doing is in fact different, and if so, how. But yeah, people don't cooperate, so this can help you use whatever data you do have. And then last but not least, my sales pitch, because you already know how. A lot of the concepts that you already know readily apply. So what's an intercept? This is not a rhetorical question. This is the audience participation portion of the program. What's an intercept? I'll take gestures too, by the way, if you don't want to type. Here's the answers. Conditional mean when all the predictors are 0, right? Expected outcome when x's are 0. Guess what? That's still what an intercept is. We're going to have a fixed intercept, which is what it is on average, and a random intercept, which talks about how it differs between people, but an intercept is still an intercept. Likewise, if I had a slope for the effect of a quantitative variable, if I told you the slope is 2, could you put that in a sentence? I'll take gestures, if not a sentence. Yeah, it's this way, right? I'm trying to get better at the backwards arm for you guys. Yeah, if a change in y for a unit change in x. So if the slope is 2, y goes up by 2 for every unit x. Yep. Guess what? That's still what a slope is going to be in this class. We're going to have fixed slopes, which means everybody gets the 2, or a random slope, which means each person is going to get their own increment or decrement to the 2. A variance around what that 2 is across people. That's what a random slope implies. But it's still a slope. What if the variable that you have the slope for is a dummy-coded variable, like a categorical variable? How do I change how I think about what the slope means? If I have a 0 group and a 1 group, and my slope is 2, what's that mean? Same thing, just switch it from 0 to 1. Correct, but I'm looking for more. So is the fixed intercept or the fixed slope the anchoring point? Yes, the intercept is the you are here sign. That's coming in the next lecture. Kind of like when we interpret interactions in the main effects. Yes, exactly. The slope is the coefficient of the coded group 1. Yes. The slope means how the one group differs from the zero group. And I have to say it that way because direction matters. If the slope is 2, the one group is higher by 2. If the slope were -2, the one group would be lower by 2. Yep, all of that is still the same. And last but not least, what's variance? And I'm not looking for the formula here. I'm looking for a concept or a gesture. Yes. Again, your tuition dollars at work, you get the extra gestures. Yes, I'm making a bell curve. Variance is dispersion. It's the idea that not everybody gets the same score. It's square root average distance of each person from the mean is sort of the technical definition. But yeah, the idea of offnesses, dispersion, spread, variance, those ideas all readily translate. The only catch is that we got more than one. So we got a residual variance like usual, that's going to be level 1. Random effects have variances. Why does everybody need a different intercept? I don't know. That's a variance to be explained. Why do people need a different time slope? I don't know. Got to explain that one too. So the catch is that we've got multiple kinds of sampling, which leads to multiple kinds of variance, which leads to multiple regression models simultaneously, one for each, which means there's also multiple R squares, one for each. So the building blocks are not different than what you already know. It's doing it all at the same time that makes it different. It's multiple. It's like regression lasagna. You know, one layer sort of feeds into the other, and each has their own purpose in the overall structure of dinner. Lasagna has a special place in my heart because it's the only thing I can cook. And that's because I used to work at a restaurant in college that was very similar to an Olive Garden. It was called Grisanti's. And I waited tables and I got tired of waiting tables. And so when I needed extra money, I started working in the kitchen and I made lasagna and I stole their recipe. So I can make lasagna, and that is it. All right. So how are we feeling about this? You feel like you can handle this? Maybe? I want to try it. Well, someday post-pandemic, we will be together again and there will be a potluck at some point. Question. So what if you didn't do it all at the same time and did them separately because you didn't know how to do them? How does that affect the estimates? It depends. If you think about the level 2 part of the model, if you just want to predict why some people are higher or lower on average, you could compute an average for each person and then predict that in a single level regression. That would be a reasonable thing to do. However, this is the however finger, by the way. This is the although finger and this is the however finger. However, when you just use a person's mean as an outcome, that mean doesn't know how it got created. It doesn't know how many occasions went into it. It doesn't know what the variability around it would have been. It's just one number. And so part of the rationale for using these models is that the outcome random intercept is a latent variable. It understands it's not perfect. And there are, how do I say this? Things built into the system if you were to try to predict it that would differentially weight those that come from more data higher than those that come from less data. Let me see where else. Okay, I think I got that. So then the reason to do it all at once is really cross-level interactions. So if you have a person per person variable that's a predictor interacting with a time varying predictor like time, you would need both levels at once to talk about how people change differently because time is level 1 and person is level 2. So that would be another reason to do the lasagna as opposed to taking it apart and just having a pile of meat sauce, a pile of cheese, and a pile of noodles. It's not as good. It's just not as good. It's not lasagna. Okay, that's the end of this. As usual, I dramatically underestimate the amount of time it's going to take me to go through stuff, so it's fine. We'll do lecture 2 next week. And there are extra examples I've linked to on the website for those of you who are less familiar with the stuff that's in lecture 2. So as we don't have any homework assignments due for quite a while, I would recommend using any extra time in addition to reading to maybe reviewing those materials as needed to get you used to using things like estimate statements, contrast statements, and that kind of stuff. All right. Any other questions or comments before we call it a day? I think it's a good place to end, don't you? 3:07 is a good enough time. I put forth the effort to make it a whole class. All right, then I will call it a day. Please take care of yourselves. Have a good weekend, and I hope to see you all next week. Office hours start now. Bye, everybody.